On the Blackboard page, there are lectures from last semester up there that have problems interspersed throughout them. So you can go on there and see more examples besides the ones that I'm going to show you today. Also, I'm going to be sending out a message that has a link to a Google document in it that has times to sign up for the class presentations. If you'll look on your class schedule, there is a list of days that we will have eligible to do the presentations, and I'm going to put up a Google document so that you can sign up for a time slot to do your presentation, and it'll update in real time since it's a Google document, and that way you don't have to worry about being double booked with somebody else. So I'll be putting that up by noon today so that you can sign up for those time slots. You do need to get signed up for a time slot as soon as possible because everybody has to present their presentation on Zoom to me, okay? So that'll be posted by noon today. Okay, so we've got 3 chapters in this unit. You'll notice I posted a bunch of segments of lectures. I've got one more piece to put up today, and then you'll have all these lecture notes. But what you'll find in this section is most of the problems are fairly straightforward if you choose the right sign for your numbers that you're given, so a plus or minus sign. So we're going to start out with some problems in chapter 18. These are going to be different than the ones that I worked before, so you'll have even more examples to look at. So we're going to start out with problem chapter 18, problem number 15. Okay, in chapter 18, problem number 15, it says a 1 centimeter layer of water stands on a horizontal slab of glass. A light ray in the air is incident on the water 60 degrees from the normal. After entering the glass, what is the ray's angle from the normal? So we've got 3 layers here, okay? So what we've got is we've got a layer of air. That's where we start. Then we have water. And then we have glass. Okay. And so what we have to do is we've got light entering in the air-water boundary at an angle of 60 degrees from the normal. Okay. So let me write down the indexes here. So N is 1 for air. For water, it's 1.33. You look this up in your book. I just happen to know what they are. And for glass, it's 1.5. Okay, you can look those up in your book. All right, now, since I'm going from a lower index to a higher index, I know that the light is going to slow down. So since N2 is greater than N1, we know the light slows down. So we know that the angle gets smaller. Before I do any math, those are things that I already know about the problem, okay? So what that means is that light, when it comes in here, instead of going on at 60 degrees, it's going to close that angle up a little bit. Now, I don't know what that is yet, but that's what I've got to find out. So I have to do Snell's law at that first boundary, okay? And so for the air-water boundary, I'm going to do Snell's law. And my dog decided to get a drink right now that I've started class. All right, so Snell's law says N of the first material times the sine of the angle in the first material, and that's always the sine of the angle from the normal, okay? So it's this angle that they've given you here. It's this angle right here. That's the angle that I want. All right. Is equal to N2 sine of the angle in the second material. So the angle that I'm looking for here, this is theta 2. Okay. All right. So I'm going to go ahead and put in what I know. So I know the N1 is 1 because it's air times the sine of 60 equals N2, which is 1.33 times the sine of theta 2. Okay, now, and I'm trying to find where I stuck my calculator. I don't see it. So I find that angle. Move my calculator somewhere. So anyway, so you can figure out that angle. Then once you have that angle, now I need to find the angle with the second boundary. So now I'm looking at the angle here. So now when the light comes in to this second boundary, I need to know this angle right here. Well, since those are alternate interior angles of parallel lines, this angle is also the same as theta 2. All right, so I can figure that out since I know I just solved for that. And so now what it's going to do is it's still going from a higher index or from a lower index to a higher index. So it's still going to slow down. And so that also means that the angle gets smaller again. Okay, so that means that the light, instead of going on through at whatever angle it comes in at, is going to be an even smaller angle. So I know that theta 3 is going to be smaller than theta 2, just like I knew up here that theta 2 was going to be smaller than theta 1. Okay, because the light is slowing down, and that's because it's going to a larger index of refraction. Okay, so I'm going to do Snell's law again for the water glass boundary. Okay. All right, so I'll just go N2 sine theta 2 is equal to N3 sine theta 3, because remember, the energy has to stay constant, and that's what that's a measure of. So I know that N2 is 1.33. I solved for theta 2, so I can put that in there. And then N3 is 1.5, and I'm going to solve for theta 3. And that'll give me the angle that it asked for, which is what is the angle from the normal after entering the glass. So you have to draw the normal at each surface, okay? You have to draw the normal at each surface. So you work each surface as a separate problem, okay? And then you get your final number there. Now, in this case, since I'm going from a smaller index to a higher index, I don't have to worry about total internal reflection. I know the angle gets smaller, so I just keep working through on that. Okay. All righty. So let's do another one. Let's look at problem number 20. This is one about critical angle and total internal reflection. It says a thin glass rod is submerged in oil. What is the critical angle for light traveling inside the rod? Okay, so basically what I've got is I've got a glass rod and then it's got oil on the outside. So what's going to happen, and I don't really need that line there, I guess. Okay, so there's going to be light inside the glass and it's going to try to go to the oil. So the first thing I need to do is I don't know what the index of refraction of oil is. So I'm going to have to go back in my chapter, and there's a chart in my chapter that tells me indices of refraction for different materials. And it says that oil is 1.46 and glass is 1.5. Okay. So I've got light coming from the glass into the oil. So since N2 is less than N1, the light is going to speed up. So the angle is going to get larger. So possible total internal reflection. Reflection. So I'll let you guys write that out. All right, now, so that means I need to find the critical angle. That's what the problem is asking me for. It's wanting me to find the critical angle. So sine of theta critical is just N2 over N1, where N2 is less than N1. All right, so you put the smaller number on top. So what happens is, if we go back to our drawing and we draw our normal to our boundary here, what happens is light comes in here at some angle, but it's going to go out at a larger angle. So theta 2 is going to be bigger than theta 1, but remember, at some point, it could get so large that it's 90 degrees and it runs right along that surface. So that's where we're looking for the critical angle. Whatever angle 1 that gives me angle 2 equaling 90 degrees is what the critical angle is. So that's how we get this formula. And we talked about that in the notes. All right, so all I need to do is put in my numbers. Oops. And then solve for my critical angle. So once I know what the sign is, and you're going to get a number 1 or smaller. If you get a number bigger than 1, it's because you got your numbers upside down. All right. Or you're using it in the wrong place where the second number is bigger than the first number. It always has to be that the second index is smaller than the first index to worry about this. Okay. So you just solve for theta critical by taking the inverse sign of whatever that ratio is. Okay. All right. So you always check to make sure that you've got the right conditions for total internal reflection, and then you just use the critical angle formula to find it. All right. Let's do another one. Let's look at a problem with lenses and mirrors. Now, in the notes, there's a whole bunch of drawings of ray tracing. So I'm not going to do a ray tracing problem here. You can go back to the videos that I posted, and there's a whole video just about ray tracing that you can go and look at. Okay. So I'm not going to do any of those because drawing them to scale on the iPad would be not worth the trouble. But I might do a quick one, but I'm not going to try to draw it to scale. But now let's work a problem first. So let's look at problem number 52. Okay, 52 says a 3 centimeter tall object is 15 centimeters in front of a converging mirror that has a 25 centimeter focal length. So they tell us a lot of stuff there. So basically what I've got is the height of the object is 3 centimeters. The object distance, which in this book they use S and S prime for that. So S, which is the object distance, is 15 centimeters. And the focal length of the mirror is 25. And since it's a converging mirror, that's a positive 25 centimeter focal length. So if you look at your sign conventions, it will tell you that. Okay, so basically, if I just draw a sketch of the problem, there's my mirror. My focal length is outside, is right here. And my image is right here, or my object, excuse me, is right here. So this is S. Okay, now, if you go to the ray tracing video and you look, I talk about what happens when you're inside the focal length or outside the focal length or whatever. In this case, I'm inside F with my object. So F is greater than S, which means now I've forced this mirror to become diverging. I've gotten too close to it and I'm inside the focal length. So now I force mirror to act diverging. Okay, so what that means is if you look at the notes, I'm going to have a virtual image because the light rays will diverge, so they won't actually cross. And that means that the image is going to form in the mirror or behind the mirror, whatever you want to say. So that tells me that S prime is going to be a negative number. Okay, it's going to be negative. All right. And I also know if I look at my ray tracing video that this thing is going to be an enlarged image and it's going to be upright. So that means my magnification is going to be positive and magnification magnitude is going to be greater than 1. All right. So if you go through that video and watch, that's how I know all that stuff. So I want to use the thin lens or mirror equation to solve for that. So the thin lens equation is 1 over F is equal to 1 over S plus 1 over S prime. You use this for both the lens and mirrors in this situation. Now, the nice thing about these problems is as long as all your numbers are in the same units, you don't have to convert. As long as they're all in the same units, they're all in centimeters, you don't have to convert. So I'm going to leave it in centimeters. So I've got my numbers. I've got what I want to know about this problem is the image position and height. Okay, so I want to find S prime and I want to find the height of the image. So to find S prime, I just do 1 over 25 is equal to 1 over 15 plus 1 over S prime. Now, I can do this a couple of ways. I can get common denominator if I want to. All right. The quickest common denominator that I see is 150 because I know both 25 and 15 will go into 150. So 25 goes into 156 times. And 15 goes into 150 10 times. So I can solve that. So I've got 6 over 150 minus 10 over 150 is equal to 1 over S prime. So that means minus 4 over 150 is equal to 1 over S prime. So S prime is negative 150 divided by 4. And that is whatever that is. So that's 150 is 30, and that's going to be 120, 130. It's going to be like 37 something. So it's going to be like 37.6 or something like that centimeters. That may not be exactly right, but you can work it out with your calculator. Okay. So, all right. So, and it's negative. All right. The negative tells me that it's a virtual image. All right. So that's my S prime. Okay. So we'll just leave it like that. And that may not be the right number, but you can work it out with your calculator. Now to find the image height, I use magnification. So magnification is negative S prime over S. That's the definition of it. All right. So I know S prime. And I'm going to actually leave it as 140 or 150 over 4 because I can do that easier. And S is 15. Okay. And so if I work that out, I get a positive 10 over 4. The centimeters cancel. So I get the magnification is positive 2.5. Okay. Positive 2.5. And I got some stray writing there. All right. So magnification is just a number. It doesn't have any units on it because the units end up canceling out because you're dividing two of the same kind of thing by each other, two distances. So the units cancel. All right. So magnification is minus S prime over S, but it's also the height of the image divided by the height of the object. All right. That's the other definition of it. So the height of the image then is the magnification times the height of the object. And they told me that the object's height was 3 centimeters. So it's 2.5 times 3 centimeters. So it's 7.5 centimeters tall. Okay. 7.5 centimeters. All right. So the 3 criteria for an image, is it real or virtual? So if it's virtual, the image distance will be negative. Is it enlarged or reduced. So in this case, that's the magnitude of the magnification. Is it upright or inverted? If the magnification is positive, it's upright. If it's negative, it's inverted relative to the object. So this, remember, is the case of like a magnifying mirror, like a shaving mirror or a makeup mirror, where you have to be close enough to it to form that image, but then you get the upright virtual enlarged image to be able to see yourself in the mirror. Okay, all right, so that was problem number 52. Let's do problem number 44. Okay, so this one says I've got a 2 centimeter tall object and it's 40 centimeters in front of a converging mirror. So my S is 40 centimeters and it's a converging mirror with a focal length of 20 centimeters. So the focal length is 20 centimeters and it's converging lens. I may have said mirror. So it's converging lens. So it's plus 20 centimeters. And they want me to find S prime and the height of the image again. Okay, so what I've got this time is my lens is converging, which means it's thicker in the middle than on the edges. So that's kind of how I draw it. Its focal length is here and my S is out here. So now I'm outside the focal length. Okay, I'm outside the focal length. So I'm going to form a real image. Okay. All right, I'm going to form a real image this time. So I better get a positive image distance this time. All right, that's one of my checks. Okay. All right. Now, the other thing that I notice is this image also, or this object happens to be sitting at my radius of curvature because the S is 2 times the focal length, which is called the radius of curvature. All right. So that's going to form an inverted, since it's a real image, it's going to be inverted, which means magnification is going to be negative. And since it's sitting at the radius of curvature, it's going to have an image that's enlarged. Because between the radius of curvature and the focal length, if you go back and watch the ray tracing video, it shows you it's going to be an enlarged image. Okay. All right. Now that may mean it's 1, magnification is greater than or equal to 1. So it may be exactly the same size or larger. All right. But it's not going to be smaller. You have to be outside the radius of curvature for it to be smaller. All right. So I'm going to use my formula. So I've got 1 over F is equal to 1 over S. Whoops, S. Got a little excited there. Okay. Plus 1 over S prime. So I've got 1 over my focal length, which is 20, is equal to 1 over 40 plus 1 over S prime. All right. So I'm going to get a common denominator again. So I've got 2 over 40 is equal to 1 over 40 plus 1 over S prime. And if I move that over, I get 2 over 40 minus 1 over 40 is equal to 1 over S prime. So 1 over S prime is 1 over 40. So S prime is 40. Okay. So if I sit my object at the radius of curvature, my image distance and my object distance are the same. So this is going to form at 40 centimeters on the other side of the lens. So that means the image is going to form over here somewhere. Okay, so for real images, it has to be on the opposite side of the lens as the object. All right, so I need to find, so there's my S prime. Now I need to find my magnification. So magnification is minus S prime over S. So it's minus 40 centimeters over 40 centimeters. So it's negative 1. So what that means is my object is inverted because it's negative, but because this is 1, that the image and the object are exactly the same size. So when I'm at the radius of curvature, which is 2 times the focal length, I get exactly the same size image as I have object. That's the only place that will happen. Okay. All right. Okay. All righty. Let's do another one. Let's see. Let's do 49. Okay. It says a 1 centimeter tall object is 60 centimeters in front of a diverging lens. So S is 60 centimeters. It's diverging. Okay. So that means my focal length now is going to be a negative number. And even if they didn't tell me that, I would know that because it's diverging, but they're nice to me and they tell me it's minus 30 centimeters. And again, they want me to find S prime and the height of my image. Okay. So 1 over F is equal to 1 over S plus 1 over S prime again. So I've got 1 over F is 1 over negative 30 is equal to 1 over 60 plus 1 over S prime. Okay. Again, I'm going to find the common denominator because I like doing those because it's easier than putting a bunch of numbers in my calculator. So it's negative 2 over 60 and 1 over 60. I'm going to move all my numbers over here. So I've got negative 2 over 60 minus 1 over 60 is equal to 1 over S prime. So that's negative 3 over 60 is 1 over S prime. So S prime is negative 60 over 3 or negative 20. Okay. So my negative tells me that it's a virtual image. Which with a diverging system, you're always going to form a virtual image. You will never form a real image with a diverging lens or a diverging mirror. Okay. All right. So magnification is minus S prime over S. So that's minus negative 20 over S, which was 60. My centimeters cancel, my minuses cancel. So I've got 20 over 60, which is 1 over 3. So my magnification is 1/3. It's plus, so it's upright. And the magnification magnitude is less than 1. So that means it's a reduced image because my image is 1/3 of the height of my object. So HI over HO is equal to 1/3. Okay. So that means that the height of my image is 1/3 of the height of my object. Okay. Can't be up here right now. Okay. All right. All right. So that's several examples there in the section on ray optics. All right. If you look at the video, I work examples out of chapter 19 and 20 in those videos kind of interspersed with the lecture. So I'm not, or not 20, chapter 17 and 19. So 17 is about physical optics. It's about like the double slit. The only problems that we would worry about in that, the only type of problem that I would have you work out of there is problems about diffraction or double slits and single slits. Okay, so I work those in the lecture portion of the notes. So you can go back and look at those. Also in chapter 19, or excuse me, 19 about the optical instruments. The only thing that I might have you work out of there is problems about the power of a lens. Like if you go to your eye doctor and get your prescription filled, or a double lens, and I work those also in the lecture notes. I work a couple of those out in the lecture notes. So we're not going to work on those too much, but we will do, let me see if I can find us a power problem that we can look at here. Now, when you talk about eyeglasses and things like that, remember that you've got near points and far points, okay? We talked about different eye problems. So for the normal human eye, the near point, in other words, the closest you can get to the eye and still be able to focus is 25 centimeters. And the far point for a normal eye is infinite. But for someone who is nearsighted, that far point is not infinity. It's whatever, wherever they can see things clearly. So their far point has been moved in. For a far-sighted person, their near point is not 25, it's further out. They can't see up close. So farsightedness and nearsightedness are conditions that are sort of lifelong because they have to do with the curvature of your eye or the thickness of your cornea or whatever. And then remember, accommodation is where the eye can no longer adjust. And so you wear reading glasses because as you get older, your far point moves out. Okay, so for people who have to wear reading glasses, that means that their far point has moved beyond 25 centimeters. So like me, I can't see, like read a book when I'm holding it at 25 centimeters because my far point has moved as I've aged. My lens doesn't accommodate, so I have to wear reading glasses. So that's a different problem than being farsighted, okay? All right, so let's see. So I worked a few problems like that, as I said, in the notes. You can go back and look at those. More of what I'm interested in for like the eye and stuff like that is you to be able to describe those conditions. So reading about those in the chapter or in the notes, we talk about color blindness or colored filters or how we have color vision. And then we talk about dispersion and things like that, where the light spreads out, where you have different index of refraction. Knowing how the basic setup of a microscope and a telescope works. We're not really going to do any problems about that. We're just going to understand how they work. I think that's more important than understanding or being able to work the mathematical part of that, because if you go into optometry, they'll have special formulas for those anyway. One thing that I'll talk about is when you talk about the power of a lens, it's 1 over the focal length, but the focal length has to be in meters. Okay, and then that gives you the power in diopters. So when you go to your eye doctor, you get a unit called a D, which is a diopter. Okay, and that's your unit of it tells you what the focal length of your lens is. Okay, all right, so that is all the problems that I was going to work on this today, because you've got the ones in your notes that you can go back and look at. I have one more little short section of notes that I'm going to post for you. Also, remember, I will post or I will email you a link to a Google document where you can sign up for the times for your presentations. So those presentations you will get on Zoom and you will present it to me. So you will screen share and present it to me during the time that you signed up for. They're 15-minute blocks of time. I'm going to put those up, and I'll probably have some during our regular class meeting time and some scheduled like on Tuesday during our testing time, since we won't have a test that week. And you can pick one that works for your schedule. And if you're working with somebody, you both need to be able to be present at the same time. All right, so you'll both log into Zoom. And so the reason I'm doing it as a Google document is so that can be updated in real time and you can see what slots are available, okay? All right, so that's all we're gonna do today. I will be posting some more notes where you can go on there and look. This video will go up as soon as I can get it posted, and you can look there. And yeah, so the way it's going to work from now on, since I have my videos that I recorded last semester, is some problems will be interspersed in the lecture. And then on Wednesday, we will do problems that are not the ones that are in the lecture. So you'll have even more example problems. So this will give you multiple examples for you to be able to look at for this next test. Okay. All righty. Thanks, everybody. And I will see you next time. Thank you for coming.